Syzygy, episode 65, Burbidge, Fowler and Hoyle. And welcome back to another edition of the Syzygy podcast. We're still in social distancing and isolation land. So currently I'm sitting in a box room in my house, very, very small recording studio. And Emily, you're across the other side of the country in a completely different place. Emily, how you doing?
Hello. I'm all good, in fact. And you can see from you can't see, but we do have some fancy Zoom backgrounds on today.
Yes, Emily's taking advantage
of wish we were elsewhere.
The recent trend, the worldwide trend in changing your Zoom background. And looks like she's currently in Astro Campus at the University of York, but you're not, are you? You're somewhere else.
No, I'm not. But it is a glorious sunny day.
Yeah, it does look rather lovely. One day you will be back in your beloved Astro Campus, but not today. Today we are recording the podcast in completely different parts of the UK, and that's fine. We're all just kind of getting on with that. So instead, in today's podcast, we're going to be talking about what is a very important paper in astronomical circles. It was one of the really big ones. Emily, what are we talking about today, and why are we touching on this subject today?
So we're talking about one of probably the most famous astronomical papers that was ever published, and we affectionately in astronomy call it B2FH or B square FH.
I would have thought that in the last 100 or couple of hundred years of astronomy, there are a few really big research findings, big research papers that have come out. So to be in the list of these, this is one of the top papers, that's a pretty good list. So what is special about this one, and why the strange name?
Yeah. So, first of all, the B square FH is just the authors' names. So it stands for Burbidge, Fowler and Hoyle.
Two Burbidges, a Fowler and a Hoyle. Yeah, Burbidge squared. So there's a couple of big names in that list.
Well, there's four big names, in fact. Names. All of these astronomers had major contributions throughout their lifetimes beyond this paper as well. But this is just, I remember my astronomy professors when I was, but a wee astronomer at undergraduate level, and we first started talking about stars and the importance of stars in the universe. And this work kind of lays that foundation, because it really, for the first time, draws together all the information that all the elements in the universe, apart from hydrogen, helium, come from stars.
So this is where that came from. We've talked about this a few times on the podcast, that all of the stuff that we see around us, the stuff that we take for granted, all the stuff that everything in this room around me is made from, and everything in me, like everything that I'm made from as well, all began in stars and were formed in stars, which is a magical idea. And this paper that you're talking about is sort of the origin of all of that. The B squared FH paper is where all of that really started to gel together as an idea. But why are we talking about this now? I mean, when did the paper come out? It's a while ago.
So it came out in 1957. Okay,
so that's more than 60 years ago. So why are we talking about this now?
So we're kind of celebrating this because the final author of the paper, who was still alive, who was Margaret Burbidge, passed away last month. And so as part of her obituaries and so on, we've been really celebrating the amazing life works that she's been doing.
Yeah, Margaret Burbidge, she was an absolute legend in the field, wasn't she? And she was, did I remember right? She was 100 when she passed away.
Yeah.
Wow. So, I mean, if this paper came out 60 plus years ago, I guess that kind of makes sense. But yes, an absolute legend in the field, and she passed away recently. And so it's time to sort of look back on that amazing achievement and her life's work. And we're going to do that through examining this particular paper. So, Emily, we're talking about where stuff comes from in stars.
Yeah, well, okay, so this is the paper that kind of really set out what we now call nucleosynthesis.
That's what I said, yeah, where stuff comes from in stars. That's exactly what I said.
So this is this idea that stars produce heavier elements, and they can do that in kind of two different ways. You have fusion and you have fission reactions. But what we're really mostly talking about is the fusion reactions that go on in stars. So this is what we call sort of stellar burning. and we have transformation of lighter elements. So things like, well, hydrogen to helium is a fusion reaction, right?
Yeah.
So they've got two smaller things, you join them together and you get a bigger atom.
Yeah. So you're talking about fusion and fission. We've got two different nuclear reactions, but the fusion is the atomic nuclei joining together with their nuclear forces to make a larger nucleus, which is a heavier element. So hydrogen into helium and on from there. And so it's the joining together, that's fusion. The fission is a really big, heavy thing falling apart into smaller things, chunks of smaller things. And those, when the large nucleus falls apart, it leaves behind bits and pieces, which are themselves smaller nuclei. So they're different nuclear processes.
Yeah. And then nucleosynthesis, the way that sits in that picture is that you're talking about the nuclei of these atoms, and you can do things like add more protons or add more neutrons, and you get different nuclei, different elements.
And what we're really talking about here is, this is all going on inside stars. It's going on inside our sun. It's where all the energy that's coming out from the sun is coming from. Right? That's where that comes from. So it's not just that's an interesting thing about stars. This is what stars do. This is what happens when you get an enormous amount of matter clumped together, compressed down by gravity, is get a lot of heat, a lot of pressure, and nuclear reactions turn on. But interestingly, those nuclear reactions are giving out energy. And I guess the way you need to look at that is that as long as a reaction can happen where you've got, one nucleus and another nucleus getting a bit too close together, the nuclear fusion can turn on. If that's energetically favorable, if energy is going to come out of that, then that is going to happen eventually. You're trying to, you've got got nuclei.
And that happens for all of our nuclei up until about iron, where you can stick two things together and you actually get an energy output from that process.
Right. But beyond iron, you can't do that.
Beyond iron, you can still stick things together, but you need to put energy into that system.
Right.
So beyond iron, you're looking for that you're making these elements in really high energy environments.
Right. And so inside a star, you're going to get eventually everything up to and including iron made, but then that sort of natural stellar process will peter out. It'll stop at that point. Is that what you're saying?
Yeah, well, that's what the energy production for the star sort of runs out at that point, right?
Yeah.
It can't, once the star starts producing iron, it can't get any further nuclear reactions to provide energy to hold it up. But there are lots of astrophysical environments, for example, supernova, where you have enormous amounts of energy kicking around with elements like iron and heavier ones as well. And in those environments, you get this nucleosynthesis of creating heavier and heavier elements because you've got lots of energy kicking around.
Yeah. So if you've got enough energy in a big explosion, you can force this. So that's presumably where all of the heavier elements that we find here on Earth have come from. Things like uranium that we dig out of the ground and do stuff with. That's not going to come from the nucleosynthesis happening in the center of the sun just by itself, but it comes from a very large supernova type explosion.
Some of it comes from supernovas, and some of it comes from, and this is really sort of some modern interpretations now that we've got amazing new observations. We also know that some of these things are produced in things like neutron star mergers.
Oh, right.
And these are the enormously energetic events that the gravitational wave detectors pick up.
Wow. I'm trying to wrap my head around that one. I mean, a neutron star, right? Neutron star is, in some ways, is where, you've gone beyond the normal ability of a star to hold itself up against the pressure of gravity. And so it collapses down and stuff on the inside basically kind of turns into one big lump of nuclear material, kind of like one big atomic nucleus. So if you've got two of those things merging together, how does that... I mean, you've got a lot of energy, but are you talking about sort of chunks of that being blasted off and forming into large or heavy elements? Is that the sort of thing you're talking about?
Right, yeah, because you've got all the ingredients necessary then, right? You might have some of your heavy elements kicking around, it's just a few of those, but then you've got all these neutrons, which is what you need to go to the next kind of heavier element. And then you've also got a huge amount of energy being released. So it's the perfect recipe.
Interesting. Okay, so this paper then, we're going... I mean, you were talking there about some of the more modern interpretations of where some of this stuff comes from, but what we were talking about a little while ago is this paper, which is, 60 plus years old, at the beginning of gelling all of these ideas together about, hey, you know what? Stuff gets made in stars. So paint a picture for us. At the time that the B squared FH paper came out, what was the picture that we had of nucleosynthesis? Was there any notion of this at all? Were they bringing the ideas together, or was it brand new?
Yeah, well, it's actually really interesting, and it's in some ways easy to forget. I mean, I've grown up my entire life knowing that nucleosynthesis, we are made of stardust.
Yeah,
this is
everyone knows this.
It's been around for ages.
Come on.
But casting our minds back to the 1940s, 1950s, this was just not the case. We didn't know where the stuff in the universe came from, right? So what we did know at the time was that all the elements, there was some thought that all the elements might have been synthesized together in the Big Bang.
Right.
So maybe just everything, all the carbon, all the oxygen, or every element that we could think of was just made, boom, at the Big Bang.
Okay, and that's a reasonable hypothesis. I mean, once again, you've got loads of energy, and that's where all the stuff came from in the first place. So, sure, it seems like a reasonable hypothesis. Doesn't stand up to scrutiny?
Well, the problem is that sort of means you've got a static kind of universe. That means the amount of carbon and nitrogen and oxygen and all these things that you've created in the Big Bang is therefore the same over all time.
Right.
And during this period, we started to make observations, and this is many of these observations were done by Margaret Burbidge, of stars. And it turns out that some stars have lots of heavy elements in them, and some of them just don't really have much at all. And it seemed to be linked to the age of the star. You could say, well, very, very young stars that were born recently seem to have lots of this kind of material in them. But stars that were born ages ago just don't have the same amount of, say, iron and nickel and these sorts of elements.
Right. Okay. Now, first of all, how were they observing that? Was it through looking at analyzing the spectra from the stars? Are they looking at these spectral fingerprints that are coming away in the starlight?
That's exactly right. Yeah. So we were developing spectroscopic techniques during these the first half of the 20th century, and this is where you break up the light into all its different wavelengths, all its different colors. You get a fingerprint from every star, which tells you the chemical elements that are inside of it. And actually, some of these spectra are in the paper itself, and you can see they were captured on glass plates back in those days. And you can see these kind of little, you see a long line, which is the spectrum, and you see tiny little gaps, and those gaps correspond to all these different chemical elements.
Wow, that's doing it old school, isn't it? There's something really quite romantic about that, about capturing data on glass plates and gazing at them, as opposed to what we do now, which is just all ones and zeros.
Yeah, so the prevailing theory at the time was that basically everything came in the Big Bang, but maybe there was some, we knew that there was some kind of alteration of this, because it was known at the time that hydrogen was fused to helium in stars, and we actually knew about two different mechanisms, the two main mechanisms that stars use to do this. So one of them is kind of a fairly direct. You take two hydrogen. The net reaction is you take two hydrogen atoms, smash them together, and you get a helium.
Right.
It's kind of, there's a few steps, but that's basically
a few steps along the way, but that's ultimately what comes out.
And the other cycle that we knew about was one called the CNO cycle. So this is carbon, nitrogen, and oxygen. Basically, they form a catalyst ring of reactions whereby you have carbon, nitrogen, and oxygen cycling round. You inject a hydrogen atom in a couple of different points, and then at the end at the end of the cycle you get helium out.
Okay, wrapping my head around that one a little bit. If you've got hydrogen and helium and carbon, nitrogen, and oxygen all kicking around, what you're saying is that there's sort of a funny fusion pattern that you can go through, where if you throw in a hydrogen at this point, then that'll create this kind of oxygen or nitrogen or something, which will then become this thing, which will become this thing, and you come back around that loop, carbon, nitrogen, and oxygen, and at the end of that, you've got all of that plus another helium has been created along the way, which is very clever.
Yeah, that's right.
very clever, and not, you wouldn't necessarily predict that going into it at the beginning. It's like, I wonder how you'd make helium. Well, if you get some carbon, some nitrogen, and some oxygen, then that's how that's going to work. So that was already known.
If you're chemically minded, this is a bit like a catalyst reaction.
In the sense that you create something new, the helium, but you haven't used up the carbon/nitrogen/oxygen. That was sort of a participant along the way in making the reaction happen. So it's kind of cool that you can have a catalyst style reaction for nuclear fusion. That's awesome.
Yeah, it's quite neat.
These things were already known.
That works in massive stars.
Yeah.
And then you've got sort of more the typical, what we call PP chain fusion, which happens in stars like our sun. So we knew about those.
Right. The PP chain is the take some hydrogen, whack it together, ultimately get helium. That's the simple one.
Yeah. So there was some, it was known that the universe wasn't entirely static in terms of the number of chemicals, because you've got hydrogen going to helium at least.
Okay.
And then in the kind of late 1940s, early 1950s, Fred Hoyle started to do work on other chemical elements. So he kind of laid quite a lot of the foundational stuff here. So that was kind of the thinking. So, and Hoyle was sort of founding, I guess, this kind of research. He had the first kind of initial papers that came out in this area. And these four people got together and started to put together this paper. I keep calling it a paper, and I thought, it's just another journal paper, and like I normally would do for a Syzygy episode, I'll pull it up and I'll give it a read and see, if there's any interesting nuggets that I can pull out of it. I pulled this one up again, and I'd forgotten actually. This paper is more like a book.
It's quite comprehensive, is what you're saying.
It's 108 pages long.
Good God. That's not a paper. That's a book. That's a thesis. That's a treatise.
Well, it doesn't have an abstract.
Right. Well,
Instead, it's got a table of contents.
What's the point of having an abstract? Like, how am I supposed to sum up this thing? Just read the paper, okay? Make yourself a nice cup of tea.
It's a review.
Clear your calendar. Yeah.
So the paper, it's a review paper that pulls together some stuff that was already published, but also, so the theory that kind of Hoyle had been working on for some time, that was in there, but also it added to this a whole lot of laboratory data on these nuclei and a lot of astronomical data on finding these nuclei in stars. So it's a massive piece of work. It's really quite incredible.
So is the importance of this paper then based around the fact that it really did pull together a huge, it sounds like an enormous amount of work, which I'm guessing is not, it's not all their own, their own discoveries, their own findings, but rather they're pulling together their work and other people's work to effectively say, here's how this works, right? They're the ones who have brought it together into a coherent whole, a coherent idea.
Yeah, well, the incredible thing is pretty much actually all their work.
Really? Wow.
Yeah. It's really amazing. And so Margaret was the first author on this paper. So that's normally the leading author who provides the most in terms of contribution, but also pulls the whole thing together and writes the majority of it as well. Astoundingly, she was pregnant at the time of writing and publication, which
is a good effort.
It's just amazing. Yeah. So I guess a couple of things I thought I would pull out of the paper, because they are important concepts and ideas that we use still in nuclear synthesis today.
Yeah, okay.
That maybe you haven't heard of and you'd like to know more about.
I definitely would. So hit me with the first one. Where do we start?
So we're going to be, most of the paper's focused on making elements that are heavier than iron. So these are the ones that you can't just bang two together and you get energy out. Instead, you need to bang things together and put energy in at the same time.
Okay. So is that because the elements leading up to iron, it was like people were already fairly comfortable with that idea, or does that come later on in the table of contents, or?
There's a bit. It's mostly sort of already laid out, but then there was some groundwork already in existence, and later work sort of built on that as well.
Right.
So I guess really the shining new stuff in the paper is all the stuff heavier than iron.
Right. All that other stuff on the periodic table that we knew was there had to come from somewhere. Well, check it out. You got 100 and something pages. Here's where it comes from.
Yeah. So the paper provides the foundational work for what we know as 3 important neutron capture processes. They're called the S process, the R process, and the P process.
Imaginative names.
Not super creative, however. So I'll start with the P process. The P process, now we're going to have to come back and remember what these atomic nuclei actually are and what they're kind of made of.
Okay.
So when you talk about the nucleus of an atom, this is the central part. We're just going to forget all about the electrons. The electrons don't really participate in these kind of reactions.
Yeah, they're a bit superfluous. They're just sort of, charged things whizzing around the outside. Ignore them. We're talking about the nucleus, which is made of protons and neutrons.
That's right. Yeah. And so if you took a particular nucleus, then you're going to have a number of protons and a number of neutrons in it, right? Now, if you add a proton to that nucleus, then you move up the periodic table to the next element.
Right, because that's what defines an element. Carbon is element number, if I've got this right, element number 8. Is that right? Does that sound right? Or is it number 6? Here, little barrel brown.
You're sitting in front of a computer, Chris.
No. It's number 6. It's number 6 because here, little barrel brown chews nuts on Friday. So oxygen is 8 and carbon is 6. That's how we learned it in school. So carbon is element number 6 because it's got 6 protons in its nucleus. It might have 6 neutrons or 7 neutrons or 8 neutrons, but the thing that makes it carbon is that it's got 6 protons, and every element, every type of stuff that we give a name to like that has a particular number of protons. And so if you add a proton, then you change the thing. Adding a proton to carbon turns it into nitrogen. Right, that's what we're talking about here. Except further up the chain, you're talking about heavier than iron.
Yeah. And in a similar way, you can add a neutron to your nucleus and you'll change it, but you'll change it in a way we call it changing an isotope.
Right. And an isotope is, so taking before with carbon, which is element number 6, as we've just established, carbon has different isotopes. They're all carbon, but they have different numbers of neutrons. So you can have carbon 12, which has 6 protons and 6 neutrons. That's why it's 12, 6 and 6. You can have carbon 13, which is 6 protons and 7 neutrons. Carbon 14, 6 and 8. They're all carbon because they've got 6 protons, different numbers of neutrons. So you can throw a neutron in there and not change the element.
Yep, that's right. So the first capture process, so this is really, instead of bashing 2 nuclei together, it's instead you've got your nucleus and we're just going to pile in some more stuff into that nucleus until it changes into something else.
Okay. And, when nuclei start getting big, they start getting a bit finicky about having extra stuff added to them. Well, I guess a nucleus of any size start squeezing too much stuff in there and they start getting a bit upset.
Yeah. So you can, for example, take your heavy element and you can add a proton to it and change it into the next element. And this process is called proton capture, or P process.
Right.
Proton.
Makes sense. Okay, I understand the naming now.
Yeah. And what you produce is something called a P nucleus.
Because it's captured a proton?
Yeah, exactly. And this happens for lots of elements from selenium up to mercury. We don't fully actually understand this P process. And in fact, yeah, there's some kind of debate even now as to exactly how these things work. But because you need to have these ultra high energy environments to even begin to study these kind of things.
What's the difficulty? I mean, he says, come on, nuclear physicists and astrophysicists. What's the problem? But you're just talking about taking nucleus and just bunging another proton in there. Like, what's the controversy here?
Well, think about what protons are.
They're very, very small, and they're positively charged, aren't they? And you've already got a lot of positive charges in there. So that could cause some problems. Yeah, I could see that. Yeah. Adding another positive charge into an already highly positively charged. Yeah. Okay, I could see how that might be a bit challenging. It's kind of difficult
to stick things together when they're charged like that, or they're charged the same way.
Fair enough. Okay, carry on.
Anyway, so that's kind of the least, to this day, it's probably still the least understood process, but we know it happens because we sort of see these P nuclei out there in the cosmos. They're more, I guess, well understood and very, very highly researched processes are the S process and the R process.
Okay, so P was proton capture. So S, I don't know. I can't even begin to guess what S and R stand for.
Well, they're both neutron captures. S is slow neutron capture and R is rapid neutron capture.
Right, so slow and rapid. You couldn't be slow and fast. You couldn't have S and F.
No, that's not allowed.
S and Q? Q's near S in the alphabet. Slow and rapid. Okay, right. Slow neutron capture and rapid neutron capture. What are we talking about?
Okay, so we have to also sort of think about these as kind of chains as well. So an S process means that you've got your element and you can change that into a different element or a different isotope, and by capturing different neutrons. But it's slow, which means that over the process of these steps, there's time for decay reactions to happen, particularly what we call beta decay.
Right. Okay. So you're capturing a neutron, right? But in the process of the overall reaction, something else can happen. A different nuclear process can happen before you reach your final result. Is that what you're saying?
Yeah. Yeah. So it happens slowly enough that these kind of decays happen. And it almost forms a little step where you add a neutron, then a decay happens, and then you might add another neutron and then a decay, or that you add two more neutrons and then it decays. So it's kind of a few stages to each of these processes.
Okay. And these decays that you're talking about, a beta type decay, that's where you can have a neutron within the nucleus can turn into a proton and along the way spit out. Now let's see, a neutron turning into a proton has to spit out a negative charge because it had no charge to begin with. It was neutral and it's just become positive proton, so it has to spit out a negative electron. Or you can have a proton, which is positively charged, turning into a neutron, and so in order to do that, it's got to get rid of that positive charge somewhere, so it spits out an anti-electron, a positron. Those are the reactions you're talking about.
That's right, yeah.
Okay.
So that's the S process. That's a slow process. And then the R process is rapid neutron capture, which means that you're kind of piling in the neutrons so quickly that you don't have chance for these decay reactions to happen.
Right. So it's like just, throwing stuff at a lump of dough. You're just adding on more and more stuff, and it hasn't got time, or it hasn't got the energy or something for these other reactions to happen. And so it's just getting bigger and bigger.
Yeah. So you're talking about really energetic and very neutron dense environments. There's a lot of neutrons around and they've got lots of energy. So these things just quick fire happen.
Right. Okay. So we've covered P, S, and now R, the different kinds of capture processes.
Yeah. And so in terms of all the elements that are heavier than iron, about half of them are formed in these R processes.
Right.
And then the P and the S process together make up the other half.
Okay, so you can take the elements heavier than iron and work your way up through them, because once you get a bit of this element, then you can sort of throw in a couple more neutrons or protons and work your way up through the chain of the periodic table to make things right through to what's the heaviest thing that we find around us on the planet? Is it plutonium? It's got to be up there.
Oh, it's one of those weird boxes at the bottom of the periodic table, isn't it?
Oh, but I thought those were
question mark boxes.
I thought those were all made in the lab. I didn't think that we don't find those around us. Yeah. Like we can make bigger ones ourselves, but I think I want to say plutonium. Anyway, it's one of those. One of those is sort of the biggest that we find before it starts getting stupidly hard.
Yeah. So this whole paper set out all of these processes. And therefore we're able to put together this picture of chemical nucleosynthesis in stars, or nucleosynthesis in stars, which means that you can explain the formation of all of the heavy elements. And again, it comes back to this kind of, we are all made of stars. So you can come back to that idea of all of the elements in your body, from the carbon to the mercury, are all made in stars.
So that's... is that the entirety of the paper then? Is laying out, all right, you want to know where these things come from? Here's where these things come from. Let's pull it all together. Is that what the 100 and something pages is?
Yeah, well, yeah. And as I say, it's built around not just the theory of how these actually work, but also the observations that all support that, which
all the data.
Incredible.
Yeah. Is it a cracking read? Is it a page turner?
I can't actually say I've read it cover to cover.
Come on. What else are you doing at this point?
Well, I skimmed through it and looked at the pictures.
Of course you did.
Actually, I did find the paper quite interesting in the sense that I was looking at it and I was thinking, this is 1957. This is before word processing. This is before the ability to make graphs and tables and things with the ease that we can do it today. And what really struck me was that the paper, it just it's in a journal which is still around today, obviously, which is reviews. Well, it's called Reviews of Modern Physics, but it's now kind of become, I think it's American Physical Society journal. And the paper just looks like a paper from today. It's quite astounding.
Amazing that they were able to do that so many years ago. Weren't they sort of carving it in stone or writing with coal on the back of a shovel or something in the 1940s, 1950s?
Oh, it's amazing. Like the tables are the same style of tables that I put into my papers. The graphs are the same style of graphs. It's done in 2 columns like all my papers.
Do you think maybe that's more of a comment about today's society than about their society back then? We haven't really moved on.
I was kind of like, yeah, we're doing it right. It's good.
Is there any difference in style? Reason I ask this is because a while ago I went and had a look at the original paper on by Watson and Crick on the structure of DNA, and it's a cracking read because it goes against all of the conventions that we tell students today about, you've got to have an abstract and an introduction and discussion and conclusion. So this is just, nope, here it is. You want it? Here it is. Bang, right there. And if you disagree with us, you suck. It's sort of, there's almost a certain amount of chutzpah about it that, wow, you really were confident, weren't you? And that's an academic paper.
Well, yes and no. I think actually it's pretty similar to how you would write the paper today. I think there's a little bit of phrasing and so on that's a bit different, and probably a little bit more assertiveness, but not significantly from what I've read so far. It's pretty amazing, yeah.
So the 4 authors, right? It's B squared FH, was it? So it's Burbidge. But presumably Burbidge and Burbidge did know each other. They were related in some way?
I think they knew each other quite well. They're husband and wife.
Okay. It wasn't a coincidence there. You're Burbidge too? That's going to be confusing. Husband and wife teams in astronomy. Is that common?
Yeah, frighteningly so.
Something to do with international conferences, maybe. So these two, did they work closely all the time? I mean, I'm guessing they did if they've done this incredibly seminal paper on their stuff together.
Yeah, I think it's certainly in the earlier parts of their careers they did. From what I can see, the later work that they did seemed to diverge a bit. So Margaret Burbidge worked, she was the observational astronomer, really. She was the one going out to the telescope, taking the plates of spectra and going and analysing those. Whereas Geoffrey Burbidge, her husband, was who was very pleased just to discover is a Geoffrey. I will like
Geoffrey. Excellent. We love a Geoffrey.
Good Geoffrey. So Geoffrey, he was more of a theoretician.
Right.
He actually transferred from kind of physics, more theoretical physics, into astrophysics after they met and got married.
Well, that's a good combination. You can get a long way with that kind of partnership if you can stand each other to the point of being able to work that closely. I don't know. I'm full of respect for people who can work at that level with their partner.
Well, some of the stories that go on are just amazing. So, well, if we start with Margaret, so this is a time when actually being a female academic was incredibly difficult. So she was an amazing groundbreaker for women in astrophysics.
Where are we talking? Where were they based?
Well, so at the time of the publication of the paper, the Burbidges were in Cambridge, Fred Hoyle was in Cambridge, and William Fowler was in Caltech.
Right, okay.
And Fred Hoyle sort of set them up in his, the Burbidges in his group, if you like, but then Fowler invited them over to Caltech to do some work on a kind of sabbatical for a few, I don't know, it might have been a year or 2 years or something like that.
But I mean, as you say, it's still today can be challenging to be a woman in an academic environment, depending on, the level of support that you find around you from your colleagues. But, back in the 40s and 50s, it wouldn't have been easy at all. So I'm imagining Margaret Burbidge had a challenging time.
Well, and indeed very directly at times, because she applied for a job as a postdoc for the Carnegie Institute. This was in the 1950s, early 1950s, before the paper. But she was turned down from the position because it involved observing at Mount Wilson Observatory. And at the time, women weren't allowed to observe at Mount Wilson Observatory. It was just...
Because why?
Just because...
Because their hormones might affect the telescopes? I mean, what's the reasoning
It
here?
might distract the men who are working the telescopes. Who knows?
Well, yes. I mean, today we might think, well, surely that's the man's problem, but yeah, this is not an unheard of thing. I mean,
No. Well, what was astounding was that this happened after, because she was obviously alive during the Second World War, and in fact, Margaret was given charge of the observatory at the university she was at, which was University of London. So she was given curatorship of the telescopes in the observatory at the University of London. Applied for a postdoc in the US, and they're like, no, don't really want you on our telescopes.
Like, thanks and everything, but no, we've got men to do this now, so you'll be fine. Thanks. Yeah, so that can't have been easy.
Yeah, but so what happened was later on, I think it was I haven't written my notes down on this one. I just read through it and thought it was kind of amusing. There was a position, I think, well, maybe it was this position whereby her husband and her swapped applications so that he was appointed as the observer at the observatory and she was appointed as the theoretician. But of course, when they actually practically got to the observatory, they switched back again.
Nice. Nice. Well, okay. I mean, whatever works. You know, again, that's a case where it's actually really handy to have someone working in a similar field to you right inside the house. You can come up with schemes like that. I like it. That's lovely.
Yeah. Although by all accounts, they had to, at the observatory, get isolated off into a different shack on the hillside. They weren't allowed to, go into the normal dorm quarters because that's where all the men were.
God forbid. Okay, so she's finally then made it into a position, though. That's good.
Yeah. And so they worked together on this paper, as I say, in the 50s. But Margaret went on to do amazing stuff. I only picked a few things, honestly, because it's quite a long list, and
a very long list.
I have to recommend the New York Times obituary because it's nicely written and it does really celebrate a lot of her work.
We'll throw a link to that in the show notes, obviously.
Yeah. One of the few things that I thought were interesting. So she was the first woman director of the Royal Observatory in Greenwich.
Mm-hmm. Which is no small thing, given, as we've just discussed, it's hard enough to actually become an observer in an astronomical institution as a woman.
Well, yeah, there's a slight irregularity there, is because up until her appointment, every single director of the observatory was also the Astronomer Royal.
Ah, okay. So up until her appointment. So she wasn't then?
So she was not granted the title of Astronomer Royal, which is a little bit...
That sucks.
Okay. Yeah.
I mean, that's got to be a great thing to do. So what do you do? Well, I'm the Astronomer Royal. Serious? Get out of town. Like, put that on your card, And she didn't even get that. That's not fair.
She didn't get that, no. I think this was in the 70s when she was appointed. Anyway, she was the first woman president of the American Astronomical Society, the AAS, which is one of the largest communities of astronomers in the world.
Yeah, that's huge.
And here's a nice one. She designed helped to design one of the instruments for Hubble.
Oh, that's cool.
Very, very cool. Yeah. So, yeah, it's amazing. There's, as I say, loads more contributions. So after working in nuclear synthesis for a while, she later worked on things like rotations of galaxies. So working out how fast spiral galaxies and elliptical galaxies rotate. She worked on quasars and at the time discovered the most distant quasar that we knew about. So amazing stuff.
It must have been an amazing time to be in and very, very senior in that field, because there was so much has been discovered in the last 50 years of astronomy. Like basically everything. We've gone from, in the last century, definitely, we've gone from like, we don't know very much at all about the universe to, wow, we've got 13.8 or whatever billion years worth of history that we know actually quite a lot about now. Like, what a time to be a senior astronomer. Just amazing.
Yeah. And what a time to be able to plow through, again, all the kind of, not even the overt, discrimination because of your gender, but also kind of toxic masculine environments, which academia was, and in some cases, unfortunately, still is.
Sometimes, yes, sadly. Impressive enough to get that kind of reputation and body of work at all, but to do it as a woman through that period in history.
Yeah. So, and the other contributors to the paper, the other people who worked on it, they also had amazing and really interesting careers as well. So
because that's just the first of the Bs. So onto the second B, Geoffrey B.
Geoffrey. So he later became famous from some of his other work with Hoyle, which is, unlike this paper, really rather controversial.
Okay.
So, well, let's talk about Hoyle, actually. We'll digress and come back to Geoffrey.
Okay. Yeah, because you did mention Hoyle's personality. Interesting chap.
Hoyle's maybe the one you might have heard of before if you're not up to date with all your astronomers of history.
Yeah, I mean, I think I've come across all of the names, all four of the names on this paper, but some stick in the mind somewhat more than others, and Hoyle's definitely up there. So tell me about Hoyle.
Well, I guess Hoyle's most famous accomplishment, if you want to call it that, was that he coined the term Big Bang.
Okay, that's why I've heard of Hoyle.
Yes. So this was on BBC Radio in 1949. He was actually criticizing the hypothesis of the Big Bang theory, or what was called explosive universe theory. I can't remember what it was called beforehand. And
so he wasn't
an offhand comment sort of called it the Big Bang, and it stuck.
So was it sort of I mean, do we really think, honestly, with a bit of an eye roll, that there was some kind of massive Big Bang? Was it that kind of thing?
That was exactly his comment.
And turns out, Professor Hoyle, we really do think that, and thank you for coining that one for posterity. We'll hang on to that. Nice one.
Yeah.
Okay.
And this is actually kind of a hypothesis that he held pretty much all throughout his entire life, that he rejected the Big Bang. He kind of, with Geoffrey Burbidge, had this kind of idea that it's more of a steady state cosmology. They even published something in 1993 that kind of talks about this theory, outlines it. They outlined a theory whereby instead of being, this Big Bang and then we're here now, it's more about the universe as oscillatory. So it kind of oscillates between different sizes, and maybe different parts of the universe expand and contract in some kind of periodic way.
So it's not saying, look, that the universe isn't expanding. We've got all this evidence that says that it seems to be. So he wasn't saying that's not happening, your eyes and your observations are deceiving you, but rather your interpretation of what that means. The idea of taking that back and saying, well, it must be that 13.8 billion years ago everything was just infinitely compressed, and so if you wind that clock forward, it was a Big Bang. He's saying, no, it doesn't have to be that way. It could be some other interpretation.
Yeah. And, this is always good to keep us in check by developing all the other things that could explain the data we have in front of us. Unfortunately, there's not really much credence that goes with this theory, at least anymore, because it just fails to explain so much of the other observational evidence we have.
Right. At some point,
it particularly struggles with the cosmic microwave background. So.
Right. At some point, the best theory has to win out. And if your hypothesis just can't hold up to the data, then sorry, it's got to go.
Yeah. But Hoyle, come back to Hoyle. He also, you might have heard of something called the Hoyle state.
Can't say I have, actually. What's the Hoyle state?
The Hoyle state is so when you talk about an atom, in this case, we're talking about the Hoyle state of carbon-12. So
okay.
Carbon, 6 protons, 6 neutrons.
Yep.
A state is a particular kind of, in this case, it's a resonance, which means that, so when you've got your helium production process in red giants, so we're talking about this hydrogen to helium, but then helium burning on further from that, then this resonance means that you can basically up the amount of production of carbon by many, many factors. So you produce heaps more carbon because this particular atom likes to resonate at this particular energy. Right.
So it's, quite a different thing. We were talking before about the carbon, nitrogen, oxygen, the CNO cycle. It's a very different process to that. But what you're talking about is, look, what's happening inside stars with fusion and with nuclear reactions is not just as simple as you whack some nuclei together and make new things. That other things come into play. And there was that catalytic behavior before with the CNO cycle. This is a resonance thing where carbon just for whatever reason, really likes this particular resonance of energy. It really likes that energy state, and that allows the carbon production process to happen at an accelerated rate. That's what you're saying.
Yeah, exactly.
Cool.
And so this explained a big problem that was known at the time with how much carbon you're producing. There was lots more carbon than original models predicted, and the Hoyle state explains, actually there's a lot more carbon being produced, so it's all good. Very
clever. Nice one, Mr. Hoyle. Good work.
Yeah. So that's also quite famous. And I guess Hoyle, out of all the authors, sort of embraced the media, embraced outreach, and did a lot of BBC work and so on and so forth. He was a real big promoter of panspermia.
Panspermia. Oh, isn't that where where the theory that life came to Earth from elsewhere? Is that the idea?
Yeah. So life originated somewhere else in the universe, but it kind of got polluted onto Earth by, I don't know, a comet or something like that.
Yeah. I mean, okay, look, plausible? Sure. Okay. It still just kind of pushes back the whole question of, okay, but where did that life come from? You can't just keep sort of cycling, well, it came from another comet. At some point you've got to grapple. But, I've heard other people talk about the same idea, and very, very respectable scientists saying, look, if you think that life began on Earth, then you're fooling yourself.
Yeah, it's only sort of more recently that I've noticed more scientists saying, maybe there's actually enough evidence to say that life independently arose on Earth. Seems to be panspermia is going a bit out of fashion, but we don't have evidence either way at this point, really.
Yeah. Okay. But he was a big proponent of that idea.
Yeah. So Fred Hoyle died in 2001. So he was actually the second author of these ones to die. Why are we doing them in order of deaths?
I don't know. I don't know. But the point is that Margaret Burbidge died just this year. What, a couple of months ago? Month or two ago?
Yeah, in April, yeah.
In April, right. Okay. Oh, it's the 1st of May. So within the last month. And she was 100, and she was the last of the people on this paper to still be around, and we're remembering her because of that incredible body of work. And I mean, that would have changed astronomy, permanently from that moment on.
Can we wind and talk about Fowler?
Oh, yeah. Because we've talked about the two Burbidges, and we've talked about Hoyle, but then there's the F, then there's Fowler.
Fowler, yeah. So Fowler sort of started out more of a nuclear physicist, maybe not surprisingly, and then became much more of an astrophysicist as his career developed. So, Fowler worked a lot with another very, very famous astronomer. And this, I actually completely had forgotten this. So when I read it again, I was like, oh, that's right. I remember that happening. Well, I remember that it happened. Fowler is the only one of these authors who won a Nobel Prize.
Oh, right. Okay.
He won a Nobel Prize, and he shared it 50-50 with another very, very famous astronomer. You want to take a stab who that might be?
Just trying to think of astronomers who've won the Nobel Prize. My brain's going blank. No, you're going to have to feed it to me.
It was Chandrasekhar.
Oh, of course. Okay. So what would that have been for? That's Chandrasekhar was black holes?
Chandrasekhar, well, his most famous piece of work was working out the maximum mass of a white dwarf star before it could collapse.
Yeah, okay.
So we call that the Chandrasekhar limit.
That's right. That's right. I knew it was something like that.
But Chandrasekhar worked on stellar evolution and the processes and physics of stars for his entire career. And a lot of that was done with William Fowler. So they shared the Nobel Prize for their overall kind of contributions to nuclear reactions and forming the chemical elements in the universe and understanding the evolution of stars.
Right. So just a little thing then, just basically contributing to our understanding of the thing that makes up, the entire galaxies of the universe. Just a little thing, just a minor increase to our
fair, if you're going to get a Nobel Prize, it's got to be for something good.
Yeah, but it does also, like I've always thought about the Nobel Prizes, and I know that this isn't a particularly original thought. I'll admit that, but it is so arbitrary that if you can have a paper like the B²FH paper, which is so transformative of a subject, so important, so big, so long, so detailed, and that doesn't get a Nobel Prize, but other things do. It's just so arbitrary.
Yeah. I mean, like many Nobel Prizes, there have been sort of comments made that maybe Hoyle should have gotten a prize because he laid a lot of the foundation for the nuclear synthesis work. Maybe Margaret should have, because she basically put together this seminal paper.
She wrote the book, yeah, quite literally.
Yeah, but yeah, I mean, the Nobel Prizes are not new to controversy about who they award them to, and overlooking women is also not unheard of.
Yeah, well, talk to Jocelyn Bell Burnell about that one. That's a story for another time. Yeah, I wonder if Jocelyn Bell Burnell and Margaret Burbidge ever went out for a drink. I'd love to be a fly on the wall for that one.
I really would like to think so. So I guess to sum it all up, I thought, why don't I leave you with the opening 2 quotations that are in the B squared FH paper, because I think they kind of summarize everything really rather nicely.
Do it. Okay.
So there's 2 quotations. The first quotation is from King Lear. If you're that way inclined, it's Act 4, Scene 3.
I know it well. I don't. That's a lie. Go on.
The quote is, "It is the stars above us govern our conditions." Now, this is the second quote, which comes from Julius Caesar, Act 1, Scene 2. "The fault, dear Brutus, is not in our stars, but in ourselves."
Very nice. Very nice. I think the art of choosing an appropriate literary allusion or quote to put in a paper or in a thesis, I guess it's an underappreciated art. And I think with those 2, they absolutely nailed it. Well, that brings us to the end of this episode of the Syzygy podcast. Emily, have you got any quotes to end us off with? That paper had some good quotes in it. You got a good your favourite Shakespearean quote to end us off with here? Just throw that one in.
I can tell you the quote from my own thesis.
Oh yeah, go on.
I don't remember the attribution, which is really naughty. Anyway, I can tell you the few lines. "The stars in order in the skies fall in silence, and in silence rise."
Very nice, very nice. Whereas, see, in my thesis, I had a quote from Einstein, and then I had a quote from Good Omens by Terry Pratchett and Neil Gaiman, and then a quote from Tom Waits. And
wow, you went to town.
If I could remember them off, they sort of form a good series. The Einstein one was God does not play dice with the universe, and then the other 2 kind of riff on that. So yeah, it was good. Probably the best part of my thesis. But there we are. Anyway, people don't want to hear about this. What they want to hear about is how...
I did have a student who recently submitted their thesis, which was working on really complex stellar modelling, trying to work out what's going on inside stars and so on. And the quote, which again, I don't remember the attribution for, but I love the quote: "All models are wrong, but some are useful."
That's good. I like that one. That's good. That's good.
So long as you find the ones that are useful, then you're all right.
Yeah. So, listen, Emily, if people wanted to get in touch with us and send in their favourite literary or scientific allusions and quotes, how could they do that? How do people get in touch with us on the show?
Well, so long as they're not too long, you can tweet them at us.
Yep.
And literally at us, because we are at SyzygyPod. Do you see what I did there?
I see what you did there. Nice work. Yeah, at SyzygyPod. But that's not the only place we're at SyzygyPod. We're at SyzygyPod in all sorts of places, aren't we?
Yes, we are on Facebook. I've been getting lots of nice updates of people looking at our posts on Facebook, so that's very nice that you still have that and you're trawling through it, maybe more often than usual, but that's good to know.
I think the social media is getting an absolute battering at the moment, but there we are. We're also on Instagram, up there on the Instagrams, and if you're not into the social medias, you can just go and check out our website, which is syzygy.fm. You can find all the past episodes with the show notes and the pictures and all of that, all the way back to episode number 1. If you want to help the show,
so we've had a nice message from David through the website, and he sent us some fantastic questions of neutron stars. They are such good questions, and they're going to take a good bit of delving into to understand. So we're going to record a special update episode to deal with those amazing questions.
That's right, David. We have heard you. We did get your questions, and Emily is busily researching away, coming up with the answers to those. And so stay tuned in the coming weeks for the special update that's gonna answer some of those. But if, like David, you want to send us through some questions, please do. And you never know, we might make a special episode or an entire normal episode about your queries. In the meantime, if you want to help the show, share it around, tell people about it, spread the word, because we'd love to rise up through the noise of the podcasting universe and spread the word of fabulous astronomy as far and wide as we possibly can. But until next time we get together over the airwaves, Emily, we're going to have to say bye-bye. So I'll catch up with you sometime soon. See you later.
Catch you later.
Bye.